550 by this talk. Today's seminar speaker and the defendant is Andrew Lohr, who will speak about several topics in experimental mathematics. In the unlikely event that Andrew will pass, we'll take him out for dinner after the talk at the usual place. If you'd like to join me, let me know. Thank you.
So, as the title says, several topics in experimental math. So, the several topics. So, first we're going to talk about tree height statistics, and this will discuss this total height statistic that you can put on any rooted tree. And we're going to look at certain classes of rooted trees and see, how the values of this statistic behave as we allow more and more vertices in this certain class of trees. So after that, we've got hypergeometric summations. There's a lot involved there. And in particular, we're going to take Sister Celine's technique for evaluating sums of hypergeometric things and expand it to types of sums that aren't quite hypergeometric, but instead this other notion, Q finite. Okay, after that, bunk bed conjectures. This is a problem where you take certain type of construction on a graph and you percolate, so you kind of randomly remove edges. And you want to, say that certain, we'll get into the details of it, but it's that certain things are connected more likely than certain other vertices are connected. And I think bunk bed is kind of cool in that it's giving this, if it were true in full, so we're only going to prove it for some subcase, but if we're true in full, it gives this credibility to the fact that you can think about connectedness in a random bond percolation model as being related to closeness in the non-percolated version. And then lastly, if we have time, we'll talk about some data we've collected on some problems in rational catalog theory. Okay, so let's start with tree height statistics. So throughout this section, we're going to be only considering ordered trees. That means that you care whether you are the left child or the second child or the third child. These are all you're not thinking about, oh, you just have 5 children, they're all indistinguishable. You're ordering your children for each vertex. Rooted just means you've got some distinguished vertexes through it. We're going to need that to talk about height. And then with allowed numbers of children S. So this means if you are a tree in the node, you can either have 0 children, in which case you're a leaf, or you can have maybe 2 children or 3 children. But the techniques are general for any S, so it could be that S is just 2, in which case it's binary trees, or it could be maybe something like that. Okay, so for each vertex, the height, that h of little v, is just the distance from that vertex to the root. And we're going to be summing over all vertices. So you can imagine if you have just some number of vertices to work with, you can get the statistic to be very small if it's very balanced. And it can get much, much larger if the tree that you're working with is very unbalanced. So in particular, we're going to imagine fixing some number of vertices and seeing what possible heights are available, and not what the actual ones are, but how is it distributed. So it could be that there are a lot of trees that have total height that's small, or it could be that more of them are kind of on the large end, the unbalanced case. So this is the problem we're going to try and investigate. So if we drop that restriction that we only have certain allowed number of children, then this was the first moment of it, right? We're going to try and analyze this distribution. We're going to analyze it through moments. The first moment was figured out by Reardon and Sloan. It's one of the very early A numbers in OAS. Has this nice expression. Asymptotically, it's n to the 3 halves times 2 root pi. Okay. I guess before this, there's the 0th one, which is the counting problem, and this is Cayley's theorem, or Cayley's formula, which is n to the n minus 1 for how many. Okay, and then more recently, instead of just looking at first moments, there are higher and higher moments, which Zalberger recently with his computer figured out, and so. Again, this has exact formulas. I think they go up through the 11th moment, but conceivably you could just keep, getting higher and higher. If you want the 12th moment, you just need to wait a little bit longer. Okay. So what we're going to do is kind of similar to the techniques of Zalberger, and that we'll be using generating functions, But they used Lagrange inversion theorem at one point, and in order to do that, they identify this, this infinite polynomial as exponential function. So we're not going to have that luxury because we're not going to have all possible numbers of children allowed. So yeah, we're going to be doing this bivariate generating function. So this means we're going to, instead of just having a single sequence counted by powers of one thing, we're going to be both counting the number of trees with a certain number of vertices and a certain total height. And then in order to peel off and look at, what is the distribution in the total heights for a given number of vertices, we can just take what is the polynomial of y that has this particular power of x in it. And we'll be looking as the x to the n. Okay. So in order to do anything with generating functions, right, just writing as a generating function doesn't really get you anywhere. What's important is to be able to do some kind of an algebraic relation on this generating function, some kind of manipulation, and from there, go back to information about the sequence at hand. So in particular, we're able to show that this bivariate generating function, this one, is going to satisfy this algebraic relationship. So just kind of walking through kind of how can you figure out at a high level how do we know that it's going to satisfy this relation? So so what we're going to be relying on is this kind of recursive definition of what a tree is. Right? This is very common when you're analyzing trees, is to use the fact that all of its subtrees are also trees, and if we can figure out how to analyze those, we can put it together and say that it's the same analysis as if we had started the current root. So the x picking the current root, that means that we're going to be counting one more vertex than if we look at all the children. Right? So this x is counting the number of vertices. And then this fxyy, why do we change this first parameter into the function? Well, that's saying, this is the first thing we pass in. That's going to be showing up every time an x would show up. So that means that if we add that factor of y in for the first guy, then every time a vertex shows up in one of your subtrees, you're counting the height as if it were one higher than if it weren't a subtree of the current thing you're working on. So you can think of that's counting the additional height that's contributed just from being a subtree of the current root. And then p, we're going to be adding over all of these possible number, we're going to be taking powers of f and adding over all of the possible ones. So adding because it's some exclusive choice for how many children does the current root have. And this exponent in I, because if we know we have I children, then we just have independent choice between the I children, what goes on in those subtrees. Okay, so once we have this, we're going to kind of massage it, restructure a little bit to a point that we can pull out the moments in y for any fixed power of x by taking partial derivatives. And the way that this goes is that we're going to, by doing the algebra, which we're not really showing here, we're going to be able to find an expression for the nth moment, say, of y, so the nth partial derivative with respect, nth moment in the total height, so the nth partial derivative with respect to y, in terms of the derivatives with respect to x of the n minus first partial derivative with respect to y.
Could you go back one slide, please, just for a moment? What's S?
So S is our allowed set of children. So we're excluding the 0 children. So we always want to allow things to be leaves. So S is if S is 2, is the second hitting 2, then you're allowed to have only 2 children or no children.
If S is a set consisting of the element of.
Yes. So in particular, we're actually able to get expressions for all of these things by doing this, having Maple take these partial derivatives and solve these systems of equations. And it's up through, in half an hour it can go up to the nth moment. And, it's only, however long you want to wait is how many more moments you can compute. There's not really any hope of getting a general formula for the nth moment will satisfy this. It's just you feed in a particular n and it's able to spit out. I guess there's also, this is one particularly nice one. It's s equals 2, right? So s equals 2 is particularly nice because the counting problem is solved for it, right? It's just going to be counted by the Catalan numbers because it's, all the possible binary trees. So since we were able to solve the counting problem, we're able to actually get concrete expressions for what the variance, expectation, skewness, all of these are. And, well, for other s's, it's not so good that we can't really figure out the counting problem that exactly. So for example, even if we go something as simple as s equals 1 and 2, right, we're allowed to have one child or two children. The counting problem there is up in, I don't know, has an A number over 100,000. It's not as, as fundamental as the counting problem for s equals 2. And it's only even a conjectured recurrence describing it. You can get a generating function for it, fine, but actually having something so concrete as we did in the s equals 2 case isn't possible. But for any other s, we're able to express what the variance, the skewness, all of these moments are in terms of the basic counting problem.
In particular, when you prove this pi is less than 10 over 6.
Yeah, that's what you're interested in.
Because minus is not.
Yeah. Okay. So, anything else to say on here? No, okay. I think that's fine. So, next big topic we're going to be covering is hypergeometric summation. So just to kind of get a flavor for like what this is, what we're trying to, the types of things we're trying to figure out. So this first one, binomial theorem.
So what was the conclusion of the first part of the talk?
So the conclusion of this is that we are able to have a computer automatically figure out expectation, variance, skewness in terms of the counting problem for given class of trees.
Yeah, symbolically they coincide with the strong view of that moment.
Yeah.
So the solution to the counting problem then is a particular sequence, like the Catalan numbers, is that right?
Yeah.
And you express the moments in terms of that sequence.
Yes.
So the way you generate these trees, quote-unquote random trees, is just all are equally likely, so you take all rooted trees and they're all equally likely,
And then
or you generate them vertex by vertex as a
Yeah,
Galton-Watson
I didn't
process.
mention, in the piece we kind of say how it relates to the Galton-Watson trees. I think kind of that's a little bit more complicated way of thinking about it because really we're considering all of the trees that could be generated for a fixed number of vertices as opposed to looking at the distribution for the total height over like some randomness that we have in the Galton-Watson process. So in the Galton-Watson process, we've got some, you imagine having some distribution on integers for each internal vertex, and you say you're going to randomly sample from that distribution and say how many kids should I have next. So you can think about this as where we only have this distribution supported on the things in S, and I'm also 0.
Yes, so when the expected number of children is exactly 1, then you can think of it as this is one way to generate all trees on n vertices with sort of uniform distribution. So the two are closely related.
Yeah. So I mean, I guess n equals 1 is like the critical probability thing that you're like expecting that it's going to continue forever at n equals 1. But I mean, you're not necessarily going to get all trees. If the expected value is 1, like you just have it's entirely supported on 1, then you're not going to get all trees, certainly. It has to also be somehow spread over, integers higher. Makes sense. Okay, good. I think maybe that's a little bit digression. Okay. Questions on the first part of the talk anymore? Okay. So this binomial theorem is kind of like the most basic thing we could talk about with hypergeometric summation. Maybe formula for just summing a geometric term, and that could also count as most basic. But we like this is probably a more appropriate one because we're going to be summing over all k. And for all of our generalizations of Sister Celine, we're going to want to have some summand that's eventually 0, so we can be summing over all k. In this case, if k is past n, summand is 0, so it's not going to be counted. And I mean, both of these are kind of trivial, but they just give you a flavor for like what is a hypergeometric summation. Okay, so why did we like binomial? So in this case, we're just having binomial coefficient, second one binomial times exponential. Like, why are they so good? And this is like one of the things that makes them so good is that when we look at ratios of successive terms as we increase n or k, we get a rational function. Okay, and yeah, so in the case of exponentials, it's just going to be a constant, and in the case of binomial, we get some linear over linear. Okay, so this is the problem that Sister Celine considered. We want to try and sum over all k these HNKs. So this is kind of almost exactly the truth, because in her work she talks about proper hypergeometric, and all this means is that you can actually express this HNK as some product of factorials over product of factorials. So this is true for binomial, it's true for exponential. X are also allowed to have exponential factors. But okay, so yeah, and again, like before when we were using binomial theorem, we were actually able to write down like here is the expression, it is equal to 2 to the n, or it is equal to 3 to the n. And well, if we're going to be allowing a broader type of thing going in, we kind of have to expect that we're going to get a slightly less pretty thing coming out. So in this case with Sister Celine, you're only really necessarily going to get this ratio of successive things coming out. You're not always guaranteed that there's a really nice formula for it. So this is from I think the 40s, Sister Celine. Okay, so moving past that, so this is kind of getting into the WZ theory of summing stuff. We're talking about, instead of just hypergeometric things, we're going to be talking about Q-finite. Sometimes you see this is called holonomic. And from like the theory of like holonomic stuff, you get a lot of nice closure properties about this. In particular, that products of holonomic sequences, or products of Q-finite sequences are also Q-finite, and different things with like the products of their generating functions also having be the generating function of a Q-finite thing, which gets you that like all of these sums, there will be some Q-finite recurrence for them, but we don't really have a way of bounding how much this D is going to be growing for under these closure properties. Okay, so yeah, so just like how in Sister Celine, they had, like, in order to allow a less friendly thing to come in, they had to allow a less friendly thing coming out. For this, we're going to say that we've solved the summation, not if we can get even a hypergeometric thing. We might get something more complicated, like one of these finite recurrences, where we have a bunch of rational functions times some finite window of previous terms. Okay. So that is what Q-finite is, and we've got a lot of nice closure properties. And so this is the kind of sums that we're going to be considering. And so what we're doing here, just like in Sister Celine, we're allowed to have some hypergeometric stuff, but we're also allowed to have a Q-finite sequence in K that we're multiplying it by to the D. So the way the details of how we actually have the computer trained to figure out this. So I guess this is like one of the big results from these chapters, that we have a computer system that you can pass this in, and if you give it enough time, it can figure out a recurrence for this thing, or say like, given your limits on how complicated your rational functions can be, or given your limits on how big of a degree we're allowed for the Q-finite thing we're searching for, we can't find something within those like limits on how complicated it can be. But more often than not, and we're always hoping that it can actually find a Q-finite recurrence. And having one of these Q-finite recurrences, apart from like the fact that like, we can't hope necessarily to do a lot better, it's helpful because there's a lot of machinery built up. If you know your sequence satisfies this Q-finite recurrence, then you can say a lot of other things about your sequence. So in particular, one that's really nice is this Birkhoff-Tirajinsky technique for computing all of the asymptotics. You say you want, the top, n terms, dominant terms in your asymptotics, it can just churn it out mechanically. So in some sense, we've solved the problem if we found that it's Q-finite, because not every sequence has a nice formula. This is one way of describing sequences where you might not be able to do it. Okay, so we have this form for types of sum we're considering, and well, wondering like, where did this come from? Why did we consider it? And it's because first we were considering this problem, and we're It's just a nice, simple combinatorial problem. It's kind of talking about like a random walk on an infinite grid. And a nice example for d equals 2 here. So we're allowed to move to any adjacent cell. So if it were 3 dimensions, you've got 26 options for your move, and 3 of the d minus 1 options each time. Okay, so we're going to solve this problem. And basically, what we're going to be doing is we're going to be reducing it to something that we can then feed into the machinery that we have in this chapter, the generalization of Sister Celine.
Right. So the problem here is.
The problem here is that we're going to start at the origin, 0, 0, 0, 0, d zeros, and see how many times or how many ways can we take a walk of length n and come back to the origin. Yeah, probably should have said that. So, for example, with 1 step, you can never come back to the origin. With 2 steps, and this d equals 2, you can have 8 ways when you step out and step back. But it gets much more complicated, as you can't really just keep counting them higher and higher. Okay, so our approach is going to be relying on generating functions again. So this is we're going to kind of show an overview of like the human side of this proof, and then we're going to get down to something that the computer can do from like that type of sum, and then we say, oh, the computer does it, magic black box thing, as far as this talk is concerned. Okay, so what we're going to be doing, instead of before where we had 2 variables, we're going to be keeping track of each dimension, how offset are you from where you started, and so by looking at the coefficient of this, we're going to be counting the number of paths from 0 to whatever each of those offsets are.
D-dimensional chessboard.
Yes, a d-dimensional chessboard.
Unrestricted.
Unrestricted boundaries.
And unrestricted paths. You don't have any constraint about.
Yeah, you can overlap your paths. Yeah. Every time you take a move, you've forgotten moves. Okay, so as kind of a very simple warm-up, what if we only had 1 dimension? And this is kind of an uninteresting problem because you can represent in the language of this, this generating function, each individual step, you're either going to be decreasing your position on this 1-dimensional chessboard by 1, or you're going to be increasing it by 1. And then we've got each of them independently, so it's just raised to the n. Okay, and central binomial coefficients, they're 2 to the n over root n. With a constant as well. So how about higher dimensions? So in this case, we're going to jump straight from 1 to d, because I mean the real work is just one was kind of too easy. Okay, so as it is, if we want to think what's happening in 1 dimension, it matters whether we stood still or not in the other dimension. So if we stand still in all but 1 dimension, then we can't stand still in that last one. So this complicates things a lot. So instead we're going to allow ourselves, okay, so here in this first parentheses, this is what a single step would look like if we didn't have the requirement that we can't stand still. And then in order to go back to the problem we had at hand, where we aren't allowed to stand still, we're just going to subtract that term off. The all standing still term. Okay, and so from this, each step is independent, so we get this nice expression. Well, I mean, it's nice in that we can notice that it's a difference of things raised to the n. And so one of the favorite tools in combinatorics, binomial theorem. We're going to take each of those terms individually, to raise to some power, and just get a nice hypergeometric thing right here. Okay, so we can see it's already starting to get kind of into the form of what we can solve with our Sister Celine term. Okay, and what we're doing here, we're noticing that we can pull the k inside. And then lastly, since this is what it is for any z1 through zd, in order to count the things that are coming back to the origin, we want to have the constant term for every dimension. Well, the constant term for every dimension, each dimension looks kind of the same. And so we're just going to be getting that same expression raised to the d. And this expression of the constant term of this trinomial is very low a number. In particular, it's one that has a known q-finite recurrence for it. So because we are able to leverage the fact that this is well studied, we can just pluck the q-finite recurrence from what other people have done. We can get it as a q-finite thing, raised to the d, times something hypergeometric. And so from there, our computer spits out all these dominant asymptotics, right? It also spits out recurrences for them, these q-finite recurrences, but I mean, it'd be a wall of text. There are some nice patterns mentioned for the recurrences, though. In particular, the degrees of recurrence, which is kind of like the more important measure of complexity. For two-dimensional, it's a degree 2. For three-dimensional, it's degree 4. For four-dimensional, it's degree 6. And I mean, see a nice pattern there already starting to form, but can't really know for sure because it can only compute for any particular d. And once we get past 4, we kind of have to rely on conjectural things too, just because of time constraints. We can't let it run forever, but there is some extra time that we could allow it to run, and then we'd be able to figure it out. Okay. Another constraint of this Birkhoff-Tirajinsky thing that spits out the dominant asymptotics is that it can't actually tell us what the C2, C3, C4 are. So all we can kind of do is get numerical approximations for what these constants out front are. Maybe one nice thing to notice is that this is a pretty intuitive expression you'd think. So a to the n over n. A to the n is the total number of paths, if you didn't care about coming back to the origin. And, well, it's square root of n to the n. Or it's square root of n in the one-dimensional case, or sorry, square root of n to the d. So it's square root of n in the one-dimensional case. We're in 2 dimensions, so we square it, cube it, raise to the 4th. And we're not losing things that actually affect the dominant asymptotics. We're losing kind of lower order things by saying we have to come back, by this different problem. Okay. So that is. So I guess I should also mention we have conjectural things for higher ones, and that's simply just by using some generating functionality to list very large numbers of these paths, and then trying to fit it to Q finite. So I think up through 8 there are conjectured recurrences, and for what that's worth. Okay, so that was like the first thing that kind of prompted us to extend Sister Celine technique to these types of sums, but it's always nice to have fringe benefits. So here, if we're going to compute the binomial transform of some sequence that we know is Q finite, we can just plug it in, no extra work, spits it right out. For evaluating multiple summations, it's also an option. So because the output of this summation is a Q finite sequence, we're given the Q finite description of the sequence, then we could then say, oh, we're going to plug that in for our xn, so we're going to say the inner sum is our xn, we know a Q finite representation of it, and so we can apply our machinery again, just iterate this. Okay, so here's just a simple example. So let's say we have the Motzkin numbers, mk, it's like the number of ways you can write chords for, if you put k points around a circle and you don't want them to overlap. They're like, I think also if you heard Brian's talk last week, he has this notion of bridges where this would be, the number of bridges you have where it's either 1, 1, 1, 0, or 1, 1, 1, 0, or 1, minus 1 for this stuff. So the important thing is though, it's something that we know Q finite recurrence for, and if we can take our problem and get it into something of this form, it could be a much more complicated thing than n choose k, but just for simplicity we have that, then the computer can spit out a Q finite description of this sum, which in some sense solves it. Okay. So I think that is it for
So
this part.
I have a question.
Yeah.
So you're saying you can compute a binomial transform of any sequence for which you have.
Well, it can try to compute a binomial transform. Yeah. It could be that maybe you need to spend way more time than is feasible to actually spit it out with the recurrences it satisfies.
Did you do any examples?
Yeah, there are examples.
It's nice.
And also n is an OIS, this particular one?
Oh, I didn't check.
Yeah, I think
Yeah, there are lots of transforms. And what's in this function?
Basically.
Okay. So next part, bunk bed conjecture. So this is something actually that I was introduced to right before my second year here, and just kind of been on the shelf and didn't really think about it much. And coming back to it, we're actually able to kind of prove a kind of a subcase of it, simpler version of it. So, but before, let's just kind of say like what the problem is. So I guess the name bunk bed should be indicative that we're taking some graph. Imagine this is like you've got one of those old cots with a bunch of springs, forming some kind of a grid. You take another one of those cots, you put it above it, and then you put a strut between each of the vertices. So each of the places on that cot, you've added some kind of we call it a vertical.